When evaluating single-phase loads on a three-phase service, each amp of single-phase load is generally considered an amp of total load. Therefore, if a 110-volt lamp fixture uses 1.3 amps, that can be added directly to the total load calculation. There is a formula used to calculate the total three-phase load from the single-phase loads. The formula is total three-phase load equals the square root of 3 multiplied by the sum of all single-phase loads. However, for typical small commercial buildings, it is acceptable to simply add the single-phase loads to the three-phase loads, as the error introduced by neglecting the square root of 3 multiplier is minimal. For further reading, consider resources such as electrical load calculations for commercial buildings available from the Department of Energy. Another resource is Three-Phase Electrical Systems Guide found on an electrical engineering portal. CALM. Practical Electrical Calculations by Roy McCormack is another recommended book. Let's delve further into understanding electrical load calculations, particularly focusing on single-phase and three-phase systems. The process involves determining the total electrical demand that a building or facility is expected to draw. This is crucial for selecting appropriately sized electrical service equipment, such as transformers, conductors, and protective devices. The National Electrical Code, or NEC, provides guidelines and requirements for performing these calculations to ensure safety and prevent overloading of electrical systems. When dealing with a three-phase service, it's essential to understand the relationship between single-phase and three-phase loads. Single-phase loads are typically 120 volts or 240 volts and are used for lighting, receptacles, and small appliances. Three-phase loads, often 208 volts, 240 volts, or 480 volts, are commonly used for motors, HVAC systems, and other heavy-duty equipment. The fundamental principle is that each amp drawn by a single-phase load contributes to the overall load in the three-phase service. Therefore, a 1.3 amp single-phase load at 120 volts directly adds 1.3 amps to the total load calculation. However, when calculating the total three-phase load contributed by multiple single-phase loads, a more accurate approach involves considering the phase distribution. In a balanced three-phase system, the loads are evenly distributed across the three phases, minimizing neutral current. However, in reality, single-phase loads are often unevenly distributed, leading to imbalances and increased neutral current. To account for this, the formula total three-phase load equals the square root of 3 multiplied by the sum of all single-phase loads can be used. The square root of 3, approximately 1.732, represents the factor that relates single-phase power to three-phase power. However, as previously mentioned, for small commercial buildings with relatively balanced loads, it is often acceptable to simply add the single-phase loads to the three-phase loads without using the square root of 3 multiplier. This simplification introduces a small error, but it is generally considered acceptable for practical purposes. It's important to note that the NEC provides specific guidelines for calculating electrical loads, including demand factors that allow for reductions in the calculated load based on the type of occupancy and the diversity of the loads. Demand factors recognize that not all electrical equipment will operate at its maximum rated current simultaneously. For example, lighting loads may have a demand factor of 100%, while receptacle loads may have a lower demand factor, such as 50% or 75%. HVAC loads also have a demand factor. These factors are outlined in various tables within the NEC, such as Table 220.42 for general lighting loads and Table 220.53 for electric ranges and cooking appliances. When performing electrical load calculations, it's crucial to consult the latest edition of the NEC and follow its guidelines carefully. Incorrect load calculations can lead to undersized electrical service equipment, resulting in overloading, voltage drops, and potential safety hazards. In addition to the NEC, various other resources can provide valuable information on electrical load calculations. The Electrical Load Calculations for Commercial Buildings document from the Department of Energy offers practical guidance and examples for calculating loads in commercial buildings. The Three-Phase Electrical Systems Guide from Electrical Engineering Portal provides a comprehensive overview of three-phase systems and their applications. Practical Electrical Calculations by Roy McCormick is a widely recognized textbook that covers various aspects of electrical calculations, including load calculations. Now, let's discuss some specific considerations for calculating single-phase loads in a three-phase system. Firstly, it's essential to determine the actual current draw of each single-phase load. This information can typically be found in the equipment's nameplate or in its technical specifications. The nameplate will usually specify the voltage, current, and power consumption of the equipment. For example, a 120 volts lighting fixture may have a current rating of 1.3 amps and a power rating of 156 watts. Secondly, it's important to consider the type of load and its operating characteristics. Continuous loads, such as lighting and HVAC equipment, are expected to operate for 3 hours or more at a time. Non-continuous loads, such as receptacles and intermittent use appliances, operate for shorter periods. The NEC requires that continuous loads be multiplied by a factor of 125% to account for the potential for sustained operation at their maximum rated current. This 125% factor is applied to the branch circuit conductors and overcurrent protection devices serving continuous loads. Thirdly, it's necessary to consider the voltage at which the single-phase loads are operating. In a three-phase system, single-phase loads can be connected line to neutral or line to line. Line to neutral loads are typically 120 volts and are connected between one of the phase conductors and the neutral conductor. Line to line loads are typically 208 volts or 240 volts and are connected between two phase conductors. The voltage must be taken into account when calculating the current draw of the single-phase loads. For example, a 240 volts load will draw half the current of a 120 volts load with the same power consumption. Fourthly, it's important to consider the power factor of the single-phase loads. Power factor is a measure of how effectively electrical power is being used. A power factor of 1 indicates that all of the power is being used to perform work, while a power factor of less than 1 indicates that some of the power is being wasted. Low power factor can lead to increased current draw and voltage drops. The NEC requires that power factor be taken into account when calculating the size of conductors and overcurrent protection devices. Fifthly, it's necessary to consider the harmonic content of the single-phase loads. Harmonics are distortions of the sinusoidal waveform of the electrical current. Harmonics can be caused by nonlinear loads, such as electronic equipment and variable frequency drives. Harmonics can lead to increased heating of conductors and equipment, as well as voltage distortions and equipment malfunctions. The NEC provides guidelines for mitigating the effects of harmonics, such as the use of harmonic filters. In summary, calculating single-phase loads on a three-phase service involves several steps, including determining the current draw of each load, considering the type of load and its operating characteristics, accounting for the voltage and power factor, and mitigating the effects of harmonics. By following these steps and consulting the NEC and other relevant resources, electrical professionals can ensure that electrical systems are properly sized and safe. Remember to always consult with a qualified electrical contractor or engineer for specific applications and to ensure compliance with all applicable codes and regulations. Finally, when working with electrical systems, always prioritize safety. Energize circuits before working on them, use appropriate personal protective equipment, and follow safe work practices. Electrical work can be dangerous, and it's important to take precautions to prevent injury or death. Consider a scenario where a small commercial building has a 240 volts, 400 amps, three-phase service. The building contains various single-phase and three-phase loads, including lighting, receptacles, HVAC equipment, and motors. To determine the total electrical load on the service, an electrical contractor would need to perform a detailed load calculation. The contractor would begin by identifying all of the electrical loads in the building and determining their current draw, voltage, and power factor. The contractor would then apply demand factors to the loads as appropriate to account for the diversity of the loads. The contractor would also consider any continuous loads and multiply their current draw by 125%. Finally, the contractor would add up all of the individual loads to determine the total electrical load on the service. If the total electrical load exceeds the capacity of the 400 amps service, the contractor would need to upgrade the service or reduce the electrical load. This could involve replacing energy inefficient equipment with more efficient equipment, implementing load shedding strategies, or adding additional electrical circuits. In some cases, it may be possible to reduce the electrical load by improving the power factor of the electrical system. This can be achieved by installing power factor correction capacitors, which improve the efficiency of electrical equipment and reduce the current draw. In conclusion, calculating single-phase loads on a three-phase service is a complex process that requires careful consideration of various factors. By following the guidelines in the NEC and consulting with qualified electrical professionals, it is possible to ensure that electrical systems are properly sized, safe, and energy efficient. Remember to prioritize safety when working with electrical systems and to always comply with all applicable codes and regulations. Understanding the nuances of electrical load calculations is crucial for ensuring the safe and efficient operation of electrical systems in commercial, industrial, and residential buildings. The principles discussed here provide a foundation for further exploration and learning in this important field. Always refer to the latest edition of the NEC and consult with qualified professionals for specific applications. Let's consider another example for further clarification. Suppose a small office building has the following electrical loads. Firstly, lighting consisting of 120 volts fluorescent fixtures, each drawing 0.5 amps. Secondly, receptacles consisting of 10 120 volts general purpose receptacles, each with an assumed load of 1.5 amps. Thirdly, a 240 volt single-phase HVAC unit drawing 10 amps. Fourthly, a three-phase motor drawing 20 amps at 480 volts. To calculate the total load, we need to consider each of these loads individually. For the lighting, the total current draw is 20 fixtures multiplied by 0.5 amps per fixture, which equals 10 amps. Since lighting is typically considered a continuous load, we need to multiply this by 125%, resulting in 12.5 amps. For the receptacles, the total current draw is 10 receptacles multiplied by 1.5 amps per receptacle, which equals 15 amps. Receptacles are typically not considered continuous loads, so we don't need to apply the 125% factor. For the HVAC unit, the current draw is 10 amps at 240 volts. This is a significant load and should be carefully considered. For the three-phase motor, the current draw is 20 amps at 480 volts. To convert this to an equivalent single-phase load, we can use the formula single phase equals I three-phase multiplied by the square root of 3. In this case, I single phase equals 20 amps multiplied by 1.732, which equals 34.64 amps. Now, we can add up all of the individual loads to determine the total electrical load. The total load is 12.5 amps for lighting, plus 15 amps for receptacles, plus 10 amps for the HVAC unit, plus 34.64 amps for the motor, which equals 72.14 amps. This is the total calculated load and the electrical service. It's important to note that this is just an example, and the actual load calculation for a building may be more complex. Factors such as demand factors, power factor, and harmonic content need to be considered. Additionally, the NEC provides specific guidelines for calculating loads for different types of occupancies and equipment. Electrical load calculations are a fundamental aspect of electrical engineering and are essential for ensuring the safety and reliability of electrical systems. By understanding the principles and techniques involved, electrical professionals can design and maintain electrical systems that meet the needs of their clients while complying with all applicable codes and regulations. Keep in mind to always consult with qualified professionals and refer to the latest edition of the NEC for specific guidance on electrical load calculations. Another crucial aspect of electrical load calculations is the consideration of conductor sizing and overcurrent protection. Once the total electrical load has been determined, it's necessary to select conductors and overcurrent protection devices that are appropriately sized to carry the load safely and without excessive voltage drop. The NEC provides detailed tables and guidelines for determining the ampacity of conductors based on their size, insulation type, and installation conditions. The ampacity of a conductor is the maximum amount of current that it can safely carry continuously without exceeding its temperature rating. When selecting conductors, it's important to consider the ambient temperature and any dirting factors that may apply. Dirting factors are used to reduce the ampacity of conductors when they are installed in environments with high ambient temperatures or when multiple conductors are bundled together. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from overloads and short circuits. These devices interrupt the flow of current when it exceeds a predetermined level, preventing damage and potential fire hazards. The NEC requires that overcurrent protection devices be sized to protect the conductors they serve. The general rule is that the overcurrent protection device should not be larger than the ampacity of the conductor. However, there are some exceptions to this rule, such as when the conductor serves a motor or other equipment with specific overcurrent protection requirements. In addition to sizing conductors and overcurrent protection devices, it's also important to consider voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to operate inefficiently or malfunction. The NEC recommends that voltage drop be limited to a certain percentage of the supply voltage, typically 3% for branch circuits and 5% for feeders. To minimize voltage drop, it's important to select conductors that are large enough to carry the load without excessive resistance. In some cases, it may be necessary to use larger conductors than required by the ampacity tables to meet the voltage drop requirements. Electrical load calculations, conductor sizing, and overcurrent protection are all interconnected and must be considered together to ensure the safety and reliability of electrical systems. By following the guidelines in the NEC and consulting with qualified electrical professionals, it is possible to design and install electrical systems that meet the needs of the occupants while complying with all applicable codes and regulations.